Yeah, but can you do the extend?
What?
The extend where we
Yeah. Yeah, there you go.
Check 1, 2.
Yeah. Duplicated it.
Just for the speaker notes, like last time.
Okay. At the end of the day, to the hub. You have to post it in.
Want that screen up all the way on the
Yeah,
board?
but here's the thing, it's showing the speaker's note. So when we do extend, it won't show. Yeah. Okay, thank you.
Is that what you wanted?
So actually, no, like last time we did extend. So what we
Yeah.
did is that we dropped this to the other desktop. Can I try to do it? Let me try to do it.
Yeah, I mean, it's on extended desktop.
Okay.
Yeah, you just gotta hit six.
Okay, 1 second. I'll do that for you.
Somebody on Zoom on their phone? Okay.
Now let's start.
Are you wearing the mic? Or are you just gonna-
Yeah,
you got
I'm wearing it.
Alright.
Yeah, I'm just.
You want this on
Okay.
just in case?
Okay, exactly. Let me but just.
Then you just gotta go, yeah. You gotta go.
But let me see how can I go to the second desktop. Okay, full screen? Oh, yeah, just hold it. Okay, perfect. Okay, so I think we can start. So, good morning, everyone. My name is Masawali. I work with Professor Bhiksha Raj. I'm his PhD student. And as you know, also, I'm your IDLTA. And today we're going to explore one of the most exciting developments in generative AI, which is diffusion models. So before we talk about specifically diffusion, let's dive into a key distinction, which is discriminative versus generative models. So anyone has any insights? What's the difference between discriminative and generative models? Yeah, please.
Discriminative is like classified classification.
Exactly. Nice job. So actually, the discriminative models, they learn to tell things apart. So they answer questions like, is this image a cat or a dog? So technically, they're computing the probability of a label given an input. Whereas the generative models, on the other hand, they learn to create new data. So the model Px, y is a joint distribution of both inputs and labels, and it can produce new samples that look like they came from the training set. So, so if we need a deeper understanding of the data distribution, so as you can see here, like in the generative models, you actually learn the actual probability distribution of the data. But, and they can do both the generative and the discriminative task, but it's also like a harder problem because it will require a deeper understanding of the distribution more than discriminative models. Who can give me like some example about these, about specific tasks for generation?
Simple as like text, images, video. Now we have worlds like games. They create 3D worlds.
Exactly, like the text generation and the image generation. Thank you. So what does it exactly mean to learn to generate the data? So imagine you have a data set of cat images, and then a generative model's job actually to learn to make a cat look like a cat. So like, what are the characteristics? What are the things like whiskers, fur patterns, and pointy ears? So as you can see, like, and then it could generate a new a cat image that never existed before, but still look realistic. And also pretty because of the data set. So, like today, we will be focused on the diffusion models, but we have like GANs, VAEs, and flow-based models. Each has its strengths and trade-offs. So GANs are fast, but they're unstable to train. The VAEs, as we talked last lecture, they're stable, but often they produce blurry images. Diffusion models are more stable, and they produce high-quality images, but they're slower. So we'll see this in a moment. So let's first do a quick recap on the VAE. So who remembers last lecture? What is the VAE?
I'm the only one who remembers.
Yeah, please go ahead. Yeah.
I think it's a combination of encoder and decoder where, both are sort of coupled. The encoder relies on what the decoder outputs, and it's a lot of Gaussians put together, and we sort of, I'm
Nice, nice, nice. Okay, who has another answer? Who would like to add something? Okay, so first of all, like the VAE has two parts, which is an encoder that compresses an image or any sample into a small latent space code. And then the decoder has to reconstruct that image from that code. So the model actually learns by trying to minimize the reconstruction error while keeping the latent space smooth and well structured. So actually, it's very elegant, but there is a problem and limitation for that. So we went through this so we can really appreciate the diffusion model. So look here. The decoder must transform a standard Gaussian all the way to the target distribution in one step. So what happens actually, it's that there's a very large gap to bridge in one step. And the second thing also is that the decoder has to do all the work at once. So the result, as you can see, you would see like blurry images, and the model averages out details because it can't afford to make mistakes in one big jump. So the natural question actually, what if we broke that jump into too many small steps instead of immediately jumping from the the full noise into the image? And that's exactly what the diffusion models do. So instead of a one giant leap from noise to image, the diffusion models take thousands of tiny steps. Each step actually removes just a little bit of noise. And because each step is small, the model can actually learn it more easily and accurately. So technically, we should view the diffusion models as a special case of hierarchical VAEs. So in a hierarchical VAE, you can stack multiple encoding and decoding steps, but the diffusion models actually make a kind of a few clever choices. So all the latent variables, they have the same dimensions as the image, and the forward process that technically adds the noise is fixed. So you don't need to learn it. You just need to learn the reverse process where you denoise and remove noise. And also these design choices made by the diffusion models are technically very, very effective. And first, Paul.
What is the phone number?
It's 1354.
Phone number is 1354.
The 1 minute. Should we break? Is there a Pikachu? Yeah. Okay, okay. Let's see which Pikachu. Is there a Pikachu? Oh, okay. Purple. Okay. I don't know. That's a weird Pokemon that I don't know. Okay, who would like to answer that, Paul? Please.
C, option C.
Exactly. So the one-step jump from noise to image actually is too hard. So the decoder can't bridge the gap accurately. So it averages, and we get these blurry images. Now here's our roadmap for today. So we'll start by defining the diffusion and explaining the process step by step. Then we will look into the DDIM, which speeds things up. And after that, we will explore the SDEs and score matching. We'll also talk about classifier-free guidance, which gives us control over what we generate. And finally, we will cover the evaluation matrix and the real-world applications. So first thing, imagine that you had a pure image and you started adding noise gradually until you ended up with random noise image. What if you had to do this process in reverse? Do you think that would be really cool, starting from fully noisy image and remove the noise gradually until you end up with a pure image? This process is the diffusion process. This is what we call diffusion process. So why is it very important? First of all, it has an exceptional generation of images, audio, and more with high fidelity. So there's a very high quality. The output has high quality, and the training is more stable compared to GANs. So it's more consistent in training the outcomes compared to other models like GANs. And let's talk now about actually the first thing which is in the diffusion, which is the forward process. So we define a forward process that actually gradually adds noise into the image over t time steps, as we can see. Where is this? We have a pointer. Does it work?
You can use the trident.
Okay. I've never used it before. Let's see if I can. Okay. So the forward process gradually adds the noise into the image over t time, as you can see, and which we denote, and also the forward process actually is denoted by Q that takes the form of Markov chain. So where the distribution at a particular time steps only depends on the sample that comes from the immediately previous step. So this is actually the forward process. And for the reverse process, the model actually learns gradually to start removing noise from the data at each step. So in the reconstruction step, we aim to reconstruct the original image or the data from its noisy version. So the main goal of training a diffusion model actually is learning the reverse process. This is the most important thing, because technically in the forward, you're just really just adding a noise. So how do we add a noise? Any thoughts? I'm memorizing faces so I can bring them coffee and cookies after the lecture.
How do you add noise? You sample from any distribution, right? And get a value, and then you add it to the SP. Well, actually, I'm not sure what you added to.
So for example, in the diffusion model, do I, for example, add noise like randomly, any kind of noise, or should I follow something? So technically here, we follow Gaussian distribution. So this means at each diffusion step, we try to inject some random noise that has a familiar distribution, which is the bell curve that we'll see in a bit. And so the standard normal sampling, we sample the noise from a standard normal distribution, which has a mean of 0 and a variance of 1. So look here. So here are the key insights, what the model actually learns. So the model actually learns to predict the noise, that was added into each step. So why is this useful? Because if you know the noise, you can start subtracting it. And subtracting noise is the same as denoising, which is the same as moving toward the clean image. So training a diffusion model is really just training a denoiser. Okay? So what could be the training objective? Who has some insights? Like, what could be the training objective if we need to predict actually the noise?
You want to minimize the difference between the two distributions, right? Of the data that you generated and the original data.
Actually, you're close, but actually, there's one thing you have to add. Why do we use the MSE? We use the MSE, actually, which is the mean squared error, but it's actually between the model's predicted noise and the actual noise. So, and in this case, we're doing so that since during the forward we're adding this noise, and we have this actual noise, and then we predict the noise, and then we use the MSE. So first of all, this high quality reconstruction, this effective training actually enables the model to accurately reconstruct original data from noise through this process. And this thing enhances actually the capability to generate high quality samples. So as you can see from this formula, that this first of all denotes the expectation over noise variables epsilon and the initial data points, which are the x0, and the time steps, which is the t. And the epsilon theta is the model's predicted noise at time t. And the alpha here actually scales down the original data by the factor alpha square root, reducing its contribution as t increases. And the 1 minus the alpha t actually scales up the noise component, making it more dominant as t increases. And the squared Euclidean norm measures the difference between the actual noise, the epsilon, and the predicted noise, which is the epsilon theta. So for the training pseudocode, what we actually do is that actually we just start with a sample from your data set. What could be the sample? The sample could be an image, audio, and you can add some noise to it, and then you can pass the noise image into your model, and then you predict the noise that was added. And then you try to minimize the distance between that and the actual noise. And you keep repeating this process until the model converges. OK, how about the sampling? The sampling means that it's like if we want to also synthesize new samples. So you need to start with a random noise. So you can pass the noisy image into your model. Then you need to predict some noise from that. And you can subtract this predicted noise from the actual noisy image in hoping to get the denoised image back instead. Paul?
Number 1355.
We should have, like, they should have posted their names. I don't know anyone's name.
Name tags.
Yeah, name tags. Even yours, though. One minute, right? Who would like to answer? C, okay. Yeah, you're right. So great. Now let's talk about a major of the DDIM. Let's talk about the limitation in the inference. So as we saw that the standard diffusion models, the DDPMs, they require running the model t times sequentially, often with t equal 1,000, and that's really slow in generating a single image that can take minutes. So the DDIM actually solves this by allowing you to skip time steps. So instead of 1,000 steps, you might only need 50. So like this is really a great speed up, like 20x speed up with similar quality. So, you know, in DDPM, each reverse step includes random noise, which is necessary because the process is Markovian, and each step actually depends only on the previous one. But, so let's see this formula for that in the DDPM. So it's the random sampling. So in the DDPM, the inference step involves actually stochastic sampling to reverse the diffusion process. So first here is the denoising function, which is the model's best guess, which is the mean or central prediction that our neural network makes at time step t. And here is the noise schedule, which is the noise level at time step t, which is the standard deviation that defines how much noise was originally added at time step t according to the forward diffusion process. It comes from the noise schedule, so the predefined plan that tells us how aggressively to add noise at each step. And here is the estimated noise, which is the model's noise prediction. This is the model's estimate of the noise that was added at times t step. And ZT as the random noise sample, so which is actually just a random noise vector that is sampled from a standard Gaussian distribution. So for the DDIM, actually, it uses a non-Markovian process, allowing for fewer steps, which actually modifies the inference step, but by modifying the reverse process, making the process more deterministic. So actually, the DDIM breaks that assumption. It makes the reverse process non-Markovian, which allows you to jump between time steps without accumulating errors. So here, the predicted x0, which is the predicted clean image, this term estimates what the original clean data looks like based on the current noisy observation. It works by taking the noisy image x and subtracting the model's predicted noise and scaling it appropriately. And this one is the direction pointing to xt, which is the term that adjusts the path we take through the denoising process. And it ensures, actually, we're moving in the right direction, not too fast, which might let us lose details, and not too slow, which actually wastes computation. And this is what the random noise. So in DDPM, we add a bit of a random noise at each step to maintain diversity and capture the full data distribution. But in DDIM, we can set the sigma to 0, making the process deterministic. This is what allows us actually to skip time steps and speed things up. Cool. Third poll, actually.
That's number 1356.
Okay, so
Anyone on Zoom want to answer that?
anyone on Zoom?
Yeah, I'll take a stab at it.
Sorry?
I said I can take a stab at it. I think it's B, that it skips time steps intelligently.
Okay, good job. So now, up to this point, we've viewed the diffusion models in a discrete way. So a sequence of 1,000 steps where we add noise forward and backward and remove the noise backward, sorry. But in diffusion models, we can also, like diffusion models can actually be viewed more generally and powerfully through the lens of continuous time processes. So this perspective actually comes from the stochastic differential equations, which is the SDEs. Why do we care? Because moving from discrete to continuous actually gives us far more flexibility. It actually also helps connect the diffusion models to a more richer mathematical framework that unifies DDPM's scored-based models and even normalizing flows. So let's start diving into this. Why should we move to a continuous time? So in DDPM, everything actually was built around a fixed list of time steps. And each step has a noise variance, and you're stuck with that schedule during the sampling. So the continuous time view removes that constraint. And instead of forcing the model into 1,000 fixed steps, we define time as continuous variable, which is between 0 and comma t, and define the noise level as a smooth function. So this gives us actually, this is the smooth function. So this is actually gives us several benefits. The first one actually is that you can choose different numbers of sampling steps at the inference time. And you can also use the ODE and SDE solvers for more efficient or higher quality sampling. Now we will go just from the ODEs to the SDEs. So the first thing is that let's connect this let's connect diffusion to standard differential equations. So in the DDPM, actually, the forward process adds noise in discrete increments. But conceptually, what we're doing actually is we're evolving the data toward the white noise over time. In continuous time, this process actually can be described using an SDE. So this SDE actually continuously pushes the data toward a Gaussian distribution as the times increases. So why does this matter? Why is this important even to think about? Because as we can see, this is the same thing, but we're seeing the diffusion model from a different perspective. So for every SDE, there's a corresponding ODE, which is called the probability flow ODE, that produces the same marginal distributions, but doesn't use the randomness. This is actually very useful for tasks like image interpolation, editing, or inverse problems, because actually it gives us a unified framework DDPM, scored-based models, and even flow models, that can all be seen as special cases of one SDE. So also the transfer insights that you can train with one method and you can sample with another. So these slides actually illustrate the difference between deterministic ODE and stochastic SDEs. So the ODEs actually evolve in a predictable path, same input, same output. And the SDE actually adds randomness. So the diffusion models use SDEs during the training, but there's something very interesting, which is you can derive an equivalent ODE for sampling. So this ODE is deterministic, which means you can generate the exact same image twice if you start with the same noise. This is very useful for things like image editing, for example. So the forward process for the SDE is that it gradually also adds Gaussian noise. The reverse process is another SDE that removes this noise. And that's what we train the neural network to approximate. So as you can see from this diagram, it shows how the forward spreads the probability mass and how the reverse process contracts it back toward the data manifold. And this is another diagram. So in the forward process, the sample becomes progressively noisier, moving toward the Gaussian prior. So as you can see here, the drift term actually pushes the x slightly toward 0. And the diffusion term here actually adds the Gaussian noise with variance, with this variance. And by time, seriously, minus 10. Okay, by time t, x is almost standard Gaussian. So also, you can see this. There's an animation for this, so I kept the link. You can see it. So for the reverse process, which is the reverse process is also an SDE, but instead of adding noise, it removes it. So however, just reversing an SDE requires one key quantity, which is very important, which is this thing, the score function. So this is the gradient of the log probability. So intuitively, it tells us which direction moves samples toward higher density areas of the data distribution. So the neural network actually learns this score function. Once we estimate it, we can plug it into the reverse SDE and generate clean samples from pure noise. So this is also the reverse process. There's also in this link animation, you'll see it in a more clear way. So I'll talk now about this, what is the score function and why does it really matters. So in the traditional generative models, they try actually to learn the density, the probability px, but that actually requires computing normalizing constant z. And sometimes that z is actually intractable for high dimensional data. So the score-based modeling sidesteps this. So instead of modeling the px, we model the delta x log px. And the good news is that here, the z disappears when we taking the gradients. So this makes the score estimation dramatically easier than density estimation. So, and if we want to connecting this to the diffusion process, Here's the connection. So we're predicting noise in DDPM. It's really equivalent exactly to predicting the score function. So DDPMs and score-based models are essentially learning the same exact object, but this is just framed differently. So for the score matching, actually, it's just a technique for training the models to estimate the score function. So it's like directly maximizing the log likelihood, which is difficult because it requires normalizing the constant z. So instead, we model the score function. And there's also the denoising score matching, which we corrupt the data with the Gaussian noise, and we train the model to recover the original clean data. This actually acts as an alternative for learning the true score function. So as you can see graphically, the model learns a vector field that pushes the noisy samples back toward the data manifold. So this is exactly what we need to run a reverse SDE. And we have also the weighted diffusion objective. So in diffusion training, different time steps have different difficulty. So early time steps have lots of noise. It's easier to predict and less important. But late time steps have little noise, and it's very hard to predict. And it's much more important. So how can we actually account for this imbalance? If we need to really account for this imbalance, we introduce a weighting function in the loss. So like some common choices is, for example, one which is simple uniform weighting. And each one of them has a different characteristics. So this one has better perceptual quality, and this one is the maximum likelihood. So this weighting actually controls how strongly the model pays attention to different noise levels. Paul.
Phone number is 1357.
I'll point to things in the end because I have many slides. Okay. Okay, so who would like to answer this? Wall? Please, go ahead. Yeah.
C.
Mm-hmm. Right, perfect. So actually the main thing in the score function that actually it points toward the high probability regions. So it's like it's like pointing toward the data. That's why following it generates samples. So now we'll talk about something very, very important, which is very needed, and we've seen now a limitation. So you've seen that in these standard diffusion models, most of them are unconditional. So what if I need to generate random images from the training distribution? But what if you want to generate a specific class, like a dog or a sunset? I need to give it like draw a sunset over mountains. How can I make this possible? Any thoughts? Any thoughts about this? Who's working on the diffusion project? Oh, we have only one person working on the diffusion project. So actually, the one option actually is classifier guidance. So maybe, like, think about this. Maybe we can train a separate classifier and use its gradients to steer the generation. But that's actually extra work, because if you train a separate classifier, you use the gradients, this will require training extra models, and the classifier could be noisy at high T. But if we have a classifier-free guidance, which train one model for both single model and better quality, we'll talk. We said that previously we had in the unconditional diffusion models, we were incapable of generating an image for a given class. So the purpose of the CFG actually is allowing for targeted generation of images by conditioning the model on a specific class label. How does that work? How does the classifier-free guidance works? So first of all, we train one model to handle both the conditional and unconditional generation. So during the training, actually, we randomly drop the condition, like 10 to 20% of the time. And at sampling time, we combine both the conditional and the unconditional predictions. So, and this scale actually controls how strongly you follow the condition. So the higher means more typical, more exaggerated examples of the class. So this simple trick actually improves dramatically the sample quality and controllability. And we'll go actually through the pseudocode of the CFG. Like, how do we really do this? So first of all, the classifier training is a classifier that is trained on both the original and the noisy versions of the image to predict the class labels. And the gradient of the classifier's prediction is actually calculated, scaled, and added into the diffusion model's output to steer the image generation toward the desired class. And the controlled sampling we adjust are the adjusted outputs that guide the sampling process from noisy to class-specific image across iterative time steps. So this is actually, and whoever is working on the diffusion project, they'll see that they're asked actually to implement this, which is very, very simple actually. So now we need to think about how we actually evaluate our models. How can we say that this output is good, or how do we really evaluate diffusion models? Any insights, any thoughts? So actually, we have different things. We have the FID, which is the inception distance. And it actually measures the distance between the feature vectors of the real and the generated images. So the lower the score indicate better image quality and similarity to real images. But there's also another score, which is the inception score. So actually, this one assesses the diversity and clarity of generated images using a pre-trained model. So for this one, we use a pre-trained model. So the higher scores denote better image clarity, and you can, like, both of these, like, you can just use the PyTorch built-in library, PyTorch matrix, and you can get all of these. And the last thing that is also very important is evaluating the quality and diversity of the generated images. So if you have a high precision, this indicates that this is a realistic image, while a high recall actually shows variety close to the actual data set. So, like, now I would talk about specific applications in the diffusion models. So the first one is the latent DDPM. Okay, before diving into this, do you have any thought why latent space? And now we will connect something to the VAE through the homework. Because actually, does any one of you actually trained any diffusion model? Did you? Okay. So actually, you would realize that running diffusion models directly in pixel space is computationally very expensive. So the latent diffusion models operate in a compressed latent space. So you're reducing the computational cost and complexity. So for the data compression, LDMs capture the essential features of high-dimensional data like images in a more compact and structured form, enhancing processing the efficiency. So the improved performance working in latent space actually focuses on relevant aspects, focuses the model on relevant aspects of the data. And this actually improves both the efficiency and the effectiveness of the generation process. So as you can see here, we map the data into latent space using the VAE. And you would realize you don't need to train the VAE. You can just use a pre-trained one or any other similar approach. So the encoder actually compresses the input data into a latent representation, and the decoder actually reconstructs the original data from the latent representation. So you would realize, if you really don't, like, whoever is working on the homework would realize that this step is very, very important, because otherwise it will be computationally very, very expensive if you don't do this. And the second thing we'll talk about is there's a paper about the stable diffusion, which is actually latent text-to-image diffusion models. And also I added the link of that paper. So we have actually many diffusion models. We have the DAL, which is a text-to-image. I think most of you knows this, which is a text-to-image generative model that actually creates coherent and high-resolution images from natural language prompts. So actually, this is also and also we have the DIT, which is also a diffusion transformer. The diffusion model architecture actually just replaces the unit with the transformers to more effectively denoise and generate high quality images. This, you can by the way, whoever is working on the diffusion project can also try this, which is very efficient. You can just replace your unit with this diffusion transformer, and you will get more efficient results. And we have also the MARV, which is an autoregressive model with diffusion loss. So, and actually now about the most important things that we went through and we covered, actually, first of all, the key takeaways is that many small steps, first of all, beat one big jump. So the VAEs try to generate in one step and fail and will produce blurry images. But when the diffusion uses like thousands of tiny steps, instead, each small change is easy to learn. So the result actually end up with sharp, high quality outputs. The forward is fixed and the reverse is learning. So the forward process is actually adding the noise using a fixed equation. So no training is really needed. And the reverse process actually training the neural network to predict the noise. And as we spoke that our training objective is the MSE. And as we saw that we can, the same diffusion model, we can have it in 3 different views. Denoising, score-based, SDEs are all equivalent perspectives. So understanding one helps us understand all. So yeah, that's it for today's lecture. And please let me know if you have any questions or thoughts or any different things.
Any questions, sir?
Yes, Mughal.
Yeah, so conceptually, I understand the difference between the VAE and the diffusion, which is that the diffusion has multiple layers, right? Multiple steps. And maybe this is a silly question, but if I would say diffusion is just a more complex VAE, would I be wrong?
So let me explain what's going on over here. Can you raise the screen?
Sure, sure.
Paul? Hold on. Here's what happens. You have some complicated distribution that you're trying to sample from, like say, there's the distribution of images. Do we know what that distribution is? Not really. It's in some high dimensional space, no idea what's happening. And so I'm just going to draw something. This is my distribution I'm trying to sample from it. And I have my VAE is going to do this. Starts with a Gaussian, he puts it through a box, and out should come this up. That's the hope.
So people in Zoom can hear.
Okay. Can you click? Thank you. So that's the hope. Now, does it succeed from the example that we saw in the last class? It doesn't succeed because basically all we are really doing is trying to learn the manifold, we're trying to learn a distribution on it. But what we are really doing is taking a Gaussian in the lower dimensional space, warping and twisting it, trying to put it in the high dimensional space. We don't quite get all the way to the end. So this is a problem. And so we hypothesized that if I could make it stage it, that this gap between a Gaussian and here is so large that this model is unable to learn it. So you can stage it, but how do you stage it? So for me to stage it, I can say I start off with a Gaussian, then I go with something that's slightly like so, then I go something like so, and then like so, and then finally, I'd like to stage it this way, right? One step at a time. Just keep moving this Gaussian more and more like towards the shape that I want. Yeah.
This is purely for, so to say, the training process, right?
I'm going forward from the Gaussian to this. And so now if I sample it and at each stage I keep adding stuff, more transforming it, the eventual samples are going to come from my final distribution. How do I know the intermediate steps? I don't know the intermediate steps, right? Okay, now what's the easiest way of, so let's try to do this the other way as well, okay? Because remember, when we trained, we want the Z and the output in pairs so that you can train everything in between, which means that I want to have the Z, and then maybe I have, I'll call this X, then maybe I'll call this Z0, then I want Z1, I want Z2, I want Z3, and then I want Z4, which is my X. I need to have every step of this process to generate, I need all the intermediate Z's, okay? Now, the way we did this for the VAE, we went from the X to the Z and then took the Z back to the X, and that step was huge. But what we know about Z is that it's Gaussian, right? X is some arbitrary distribution. What's the easiest way of making an arbitrary random variable Gaussian? What's the easiest way of doing it?
Scale it.
Scale it. Will scale it make it? Scaling it make it Gaussian? Then what will make it Gaussian? Adding? What kind of noise? You want to add Gaussian noise, right? And so do I have an eraser? And so here's what we want to do. I know that if I add a massive, one way of making this a Gaussian, so I have my complicated distribution. I want to make it a Gaussian. I want to make this Gaussian back a complicated distribution. And we know that this jump is huge. We were trying to learn this through some crazy neural network. It does a half-assed job. So let's do this do it a different way. I'm going to add a massive amount of noise to this and go here. But if I add a massive amount of noise to this and go here, can I come right back? I've lost all the information. So I'm going to stage that as well. Here's what I will do. I'm going to start off with this guy and add a little bit of Gaussian noise. If I add a little bit of Gaussian noise, what happens?
You're getting slightly closer to the natural.
If I add Gaussian noise to this, it's going to look a little more Gaussian, right? If I scale it, if I don't scale it, the variance will keep increasing, so I'm going to scale it to keep the variance fixed. It's going to become a little more Gaussian, okay? And so maybe this guy ends up becoming like so, slightly smoother. And now this difference is very small. I'm going to try to learn how to go back from here to here. Because I've just added only a little bit, right? It's easier for me to learn how to go back from the slightly more Gaussianized distribution to the original distribution. That making sense? Right? And then this is but this is not Gaussian, right? And I'm going to need some way of characterizing it. So now I add a little more noise. And so then it's going to become maybe slightly more Gaussian, right? And now I have done this. I know how to go back. I know how I've come from here to here. I'm going to learn how to go back here. I keep doing that. Eventually, what will I end up with? I'm going to have a Gaussian. Have I learned how to undo every single step? Yes, because at each point, I've actually just been undoing things, right? Now, which is the more challenging bit? Adding noise and making it more Gaussian, or going back from the more Gaussian thing to the original one? Going back to the original thing. So the forward process is very straightforward. You just keep adding trickling bits of noise into the distribution. And as you do this, it becomes flatter and flatter and more Gaussian. And at each stage, you're learning how to do the reverse. Yeah?
Are we going back to T0, or is it sort of?
I don't know about the symbols. I don't know about the indices. Every time I read it, I get very tangled with the symbols. So I'm not going to use the symbols. You get the concept, correct? I don't know what is T and what is T0.
No, what I meant to ask is, let's say you are on the 5th time step. Are you going back all the way to the?
Forget about time, right? They like to use this notion of time because you like to think of this as an animation. I start off with this crazy distribution, it just becomes a Gaussian, then the other way it goes back and looks like this shape. And I can draw little videos and animations and show you how this happens, but that's not really giving you much of a picture of what's going on. The real thing is that you are adding little bits of Gaussian noise at each step. It becomes a little more Gaussian. You're figuring out how to undo this, right? Then you do the same thing over here. You add a little more noise, you figure out how to do this. Now it's 2 steps, right? And if you stop at any point, it's not Gaussian. So you have to do this a sufficient number of times so that in the end it looks reasonably Gaussian. And then you can go back. Is that making sense to you guys? Right? And so that's the whole process. That's the entire diffusion model. And going forward, you really have very little to learn in the going forward. The only thing you have in the going forward stage is how much noise you add at each stage. That's in your control. That's your, what do you call this? The schedule, right? You schedule the noising as you go forward, and then you learn to undo this going backward. Make sense? Right? That's the diffusion model, period. Now, then of course, what is an SDE and what's an ODE over here, right? What you're really doing is you're taking this, and if I make the steps smaller and smaller and smaller and smaller, what will you get in the limit? It's a continuous change at some point, right? If I keep making the steps smaller and smaller, I'm making this a continuous change. If I have a continuous change, how do I characterize this? These can be characterized using differential equations. That's where, so basically because you're adding noise is a stochastic process. You're adding noise. So when you're going from, lady there, can you turn your phone upside down? Should I ask you to leave the class? Turn the phone upside down. If you don't want me to, turn it upside down and put it in your bag. If you don't want me to be rude to you, don't be rude to me. Okay? This is the last time I'll let you turn the phone upside down. The next time I find somebody with a phone on, you will leave the class. All right? Okay. So anyway, so that's the whole process. And so as I keep making these steps smaller and smaller, in the limit, I'm going to end up with a differential equation. It's stochastic because the process of morphing it to a Gaussian is adding noise, right? The process of taking it back is removing noise, right? It's not removing noise, really. Now, I want you to tell me this. Can I add Gaussian noise to any random variable and make it less Gaussian? Not really, right? Which is why you have so the way the diffusion model is set up on the decoding side is that you actually make it a little more Gaussian and then transform it using one step of the decoder to make it even less Gaussian. So the decoder is a crazy funky thing. And if you try to do this without adding noise, you get an ordinary differential equation. If you add noise, it becomes a stochastic differential equation. That's it, right? Those are the 2 things. So where does conditioning come in? So once I give you this idea, do you really need to learn a lot about how to figure this out? Once you know this basic idea, once I've given you this idea, do you think you could code it? It should be very easy for you to code it, or at least some half-assed variant of it. Why? Because what are we doing? All I'm doing is starting with I'm adding Gaussian noise, right? I could start with an image. I add a little bit of noise. I get a slightly more Gaussian data. So I have XZ pairs, correct? Can I learn a reverse mapper?
Yes.
Yes or no?
Yes.
Right? Because I have this X here. I added a tiny bit of noise. And then I made this, I'll call this what did they call it? XT, whatever they call it, right? I think they call it X0. I'll call it X0, right? And so then I have X1. So by adding noise, I've got X1. You know how to train something that goes back. Correct? By adding noise, I make this X2. You know how to train something that goes back. I can further say that the network that goes from X2 to X1 is the same as the network that goes from X1 to X0. So you have shared parameter networks. This still hasn't changed anything, correct? Mohammed, make sense?
Yeah, until you said that is shared, it's the same network that would learn how to go from x2 to x1 is the same as x1 to x0.
Yeah. Hmm?
How does that work? How do you do it with the same network?
So how do you do it with the same network? I just say x2, x1 and x1, x0 are two training instances to the same network, right? Now is that hard? That explain? Yeah.
Aren't you learning a different distribution of
I'm just learning how to modify, take the noised version back to the less noised version. That's all, right? That's all I'm doing. And so at this point, with just this much and without any of the additional math, you guys should be able to figure out how to write yourself a diffusion model, right? Because you can just keep adding noise. I can have the entire sequence, x0, x1, x2, x3, x4, until you think that the thing is actually going to be Gaussian. You can create, the x0, x1, x1, x2, x2, x3, x4, x5. These are all your training instances. You just throw them in, you train a network, you're going to be able to figure out something that goes all the way back. Yes or no? Right? There's nothing complex about this at all, once you think about it this way. That's your classic DDPM or DDIM. I'm bad with terminology, right? And you can make these steps. Now, once you want to make these steps a little bigger, then you have to be a little more careful, right? And so that's where the other DD, what the other M thing comes in. And now the other thing that you have to worry about is how do I make it generate data of a specific type? So I'm training this image on this network to transform Gaussians. Okay, did everything I say so far make sense?
Yeah.
Right? So now, yeah.
Just to make sure I understand the answer to my specific question, it was the reason why we're doing this small increment is that it's easier to learn it, right?
It's easier to learn it, and you're doing this in a guided way. Otherwise, the step becomes large, and you're back to where you began.
Right.
With the, with the VAE.
So essentially, they're similar, but this is rather than doing one big step, which is really hard, we're splitting it.
Furthermore, when you go from X to Z, instead of learning a network that goes from X to Z, you explicitly do it by just adding noise yourself. That's all, right? So that's much more controlled, and you can decide exactly how much noise to add. Make sense? Yeah.
Is the learning incremental? So if you have already learned x0 to x1,
no, but again,
sufficient?
No, because x0 to x1 is the same as x1 to x2. So it's not really incremental. It's all at once. So, but in terms of training, there's really nothing fancy that's going to be going on over here, correct? Yeah.
If the whole motivation for doing this incremental step was that a VAE does too big a jump, then for the latent diffusion model, why put a VAE to make it jump to a latent space and then do this?
Okay, you tell me this. Do I need to go all the way? If I'm taking many small steps, correct? At each point, I'm living in the same dimensional space as the original data itself because I'm just adding a little bit of noise. What was the problem with the VAE? The problem with the VAE was that it wasn't able to make a big enough jump. But how about using the VAE as the initial seed?
So implicitly reduces the size of the jump.
Yeah.
Okay.
Right, so the VAE sitting in the middle is your initial seed. You're going from whatever to Z, which is a lower dimensional back up. And now, because the VAE is really easy to train, you've gotten rid of a whole chunk of training, and now you can work in the lower dimensional space. That make sense? Right? So that's basically what the latent diffusion model does. Right. Now, that leaves us with this business of, did all of that make sense? Zoom, did that make sense to you guys? Is there anybody left on Zoom?
Yeah.
Yep.
Nobody else. Yeah, okay. That makes sense to you guys, what we were just saying. Yeah. I don't think they were hearing. Yes?
How come like regular DEPM doesn't have latency?
So you don't need, you're eventually in the Z. The Z is a latent space at some point, right? It's just that it's as the same size as the original data itself. When you have a latent diffusion model, you actually reduce the dimensionality using the VAE right in the middle. Does that answer your question? Right? And so, but then if I want to condition things, if I've trained this model using lots and lots of images, and then I'm sampling it to generate a new image, how do I ensure that the new image is a cat? How do I ensure that the new image is a cat?
Take samples which have a cat and those who don't have a cat.
Here's a very simple thing. I can look at the output and say, is this a cat? Can I not? What does that tap? What does this? What kind of automated operation will look at the output and say, is this a cat? A classifier, correct? And so now I can actually classify the output of my network. And then if I find that it's not what I want it to be, I have a loss, right? How far away I am. Now again, the denoising process is actually introducing little bits of noise. What is happening over here? I have this Gaussian at the input, and out comes a distribution which is like the distribution of cats, which is going to be some funky shape, right? But if a distribution of images in general, and in this region represents cats. So if I look at the pre-image of that, that's going to be something out here, right? And somehow I have to make sure that I'm pushing things to be sampled from there. So what I'm really doing when I have a classifier guided reconstruction is that I'm going to be using this loss to be pushing the noise terms that I add and the transformations that I have, such that eventually I'm focusing on just the portion of the input that generates cats. And the classifier free guidance is, I think I'm a little unclear exactly how that works. So, but in the case of the CF classifier free guidance, you're basically looking at increments as opposed to having a classifier at the output. Maybe she can explain. Right? Is that what we do? Yeah. So in the classifier free guidance thing, you're just saying, what do I get if I have a generic response, and if I have a generic output, and what do I get if I'm looking at an output when I'm specifically asking you to produce cats, right? Sure. And so this, and then the difference is really telling you how far away you are from cats, and use that to guide the model. But overall, literally with just a little bit of English I gave you, you guys should be able to go off and train a small diffusion model, because it's not hard. Yeah.
And the fact that once we take those steps, if you make the steps very small, we have a continuous model. So that's why we have this stochastic, which is why now when we want to do the classifier, we can just use the difference as opposed to having to do actual classification.
Yeah. But you can do that. You don't even need an SD or an ODE for that. You can just, So again, you can think of it this way. When I'm just doing this, the standard stuff, standard diffusion model, I'm modifying this one step at a time to this guy. When I'm using an SDE, it's continuously morphing to become the other guy, right? And on the input side, I'm going from this this funky distribution to a Gaussian one step at a time. Whereas if I'm using an SDE, it's just continuously morphing to the Gaussian. That's the only difference. In a classifier guided generation, you're looking at the output and saying, is this a cat? In a classifier free model, you're actually going to be providing these labels at training time. You're going to say, okay, here's what happens when I tell it to produce something, and here's what happens when I ask it to specifically produce a cat. So let's minimize the difference between the two, right? Any questions? Yeah.
You're still learning a manifold in this process.
You're not learning a manifold unless it's a latent VAE, right? I mean, you're implicitly learning to produce things on the manifold. Okay. But you're really just saying, how can I go from a full dimensional Gaussian to a full dimensional image, right? And you just got rid of the whole manifold concept over there. Again, you will be learning a manifold. Basically, what the model is going to be doing is going to be chopping every part of the full Gaussian distribution after transforming it, right? And so,
because my intuition was telling me, like, I'm basically learning the noise, sort of. How do you add?
So a different way to think about it is that in my input space, I have a Gaussian distribution. It's going to be something of this kind, right? It's full dimensional because it's an isotropic Gaussian. Then as you go through the network, it's projecting it down slowly, flattening and reshaping it so that it lies on the manifold. Does that answer your question? Yeah. You don't have to explicitly, the nice thing about the diffusion model is that you don't have to explicitly guess the dimensionality of the manifold. Whereas if you have a VAE, you have to guess the dimensionality of the manifold. By doing this one step at a time, you're hoping that it's squishing it in all the right ways so that it learns the dimensionality of the manifold without you specifying it, which makes it a better model in many ways, right? Any other questions? No? Yeah.
In the simplest terms, adding noise, what does that mean? Are we randomly sampling?
I'm literally adding noise, right?
And it's a scalar that.
No. Okay. How do I sample? Say I have a 1,000,000 pixel image, right? What would a noise be?
1,000,000 pixel image.
Yeah.
Changing the RGB value.
So basically, a noise is simply going to be a 1,000,000 dimensional vector drawn from a Gaussian. That's it, right? It's going to be a patch of rubbish if you plot it. If you think of it as a vector, it's a 1,000,000 dimensional vector, right? Basically what Norman says. He's speaking of RGB, I'm speaking of grayscale with the same thing. That answer your question?
Yes.
Yeah. Anything else? All right, guys, thank you.